So I was helping some people, and I think a lot of people have the same questions. Figured I'd make a little video over cycle, the project 2, the initial cycle. It's pretty basic stuff, but it's for people who have not actually used EES before. Hopefully you can see everything on my screen perfectly at this point. So I drew out the basic cycle 1 with the heat exchanger at the top. It goes to a turbine, hits your work out, goes to a condenser, and then goes to a pump back to your evaporator slash heat exchanger. According to the project, we were supposed to say that this steam was 950 degrees Fahrenheit at 1250 psi going into the turbine. And at the end of the turbine, it was 27 inches of mercury, and this heat exchanger was 108 degrees Fahrenheit. If we assume that this is a phase change going on down here, that would mean it would be 108 degrees Fahrenheit at state 2 going into the heat exchanger and state 3 coming out of this heat exchanger. Instead of using the 27 inches of mercury, I looked it up and it's around 1 point something psi. Instead, in ease, I can just use the pressure function for water. So I'm saying pressure, and I have to tell it the fluid, which is water, comma, I have to give it a condition. So T equals 108. Down here at the bottom, I've set my units to Fahrenheit and psi, absolute. Besides the temperature, it also needs to know one other condition. So I could give it something. I could use pressure instead of temperature, but inches of mercury is a little weird. Instead, I'm going to give it quality. So X equals. Now, if it's quality between 0 and 1, that means it's in a two-phase region on the TV diagram. And if, as we said with this heat exchanger, it's got a phase change going on. So I'll just give it a quality of X equals 0.5, which means it's right in the middle of the phase change region. As it's coming out of the turbine, that's probably not likely, but this won't actually affect the pressure because the pressure should be constant. So I'm going to hit run, and we get 1.204, which is pretty close to what you would say if you just Googled 27 inches of mercury into psi. So instead of using the low pressure, I'm going to use temperature. If I used X equals 0.9 as it was 90% vapor, we'd still get 1.204 because it's a constant pressure. So I don't need this 27 inches of mercury. I'm going to operate on the assumptions that state 3 is at 108 degrees Fahrenheit, and I'm going to also say state 4 is 1250 psi because everything on this side of the pump on the top side is at the same pressure, and everything at the bottom is at the same pressure. For ES code, it's really not too difficult, and like Dr. Hagges says, it's better to build it in steps. Generally, to keep my code clean, I'll put variables at the top, and I usually soft code everything. So instead of typing in water, I'll put a variable at the top, say fluid $1 equals, do little single quote marks, and then I can type in water. Then I can easily later on change this water to nitrogen, air, or something else, and it'll change all the variables in my code. Also, you're going to need to use efficiencies. So efficiency of, you could just have one efficiency. I like to have multiple efficiencies and change them each variable. So efficiency of a pump, maybe I usually around 80%, so 0.81, and efficiency of a turbine equals, I don't know, 0.8, something similar. And I'll go ahead and throw in some initial variables. T1 equals 950 degrees Fahrenheit. P1 equals 1250 degrees Fahrenheit. And I can even call up P2, that pressure after the turbine. Now I'm going to have to use my function, so pressure, and in this case I'm going to do fluid 1, and I have to give it its two conditions. So I can say T equals 108, or I could say T equals T2. And then T2 can be changed later on, so I'm going to add T2 up here as 108. And now I'm going to go ahead and give it an X equals 0.5 quality. I'm hard coding in the quality of the water because it's not going to matter if it's 0.1 or 0.8. Let's go ahead and hit run, and I'm getting P2 to be the 1.204, so that's good. Quotations will let you comment something out. This is a comment. This is pretty useful for making your code readable by other people. If we hit run or check mark, it turns blue. The other thing you can use is the square brackets here, and you can bracket out a lot of equations at once. So if I just square bracket out a chunk and I hit run, it stays blue. It doesn't actually appear if I actually run no T5. That's useful for troubleshooting. So to make our code readable, you need a diagram on the right here. Otherwise, you're just floating equations in the middle of the air. I've numbered my states 1 through 4 over here. I could have started the number 1 in the top left, but I started in the top right. So state 1, I'm going to call it the 1-2 turbine out workout. This tells me that if I'm looking at this paragraph of code, I need to look at this turbine, and I'll be able to see if all my stuff makes sense. So at state 1, I have 2 facts: Fahrenheit, the temperature, and the pressure. So I can write H1 as my variable, so I could use any variable, but H enthalpy and state 1, H1 seems good enough to me. So now instead of pressure, like, you have a bunch of different word functions, so enthalpy. And now fluid, $1. I could easily have just wrote water, but then I wouldn't be able to change water to any other fluid I wanted. So I'm just going to use my fluid variable. I need 2 conditions, so T equals, now instead of 950, if I want to change that later, I'm just going to do T equals T1. And instead of typing in 250, I'm just going to write P equals P1. So H1 is going to be called off of the state conditions of state 1. Let's hit run. H1 is right here, 1469. So a lot of enthalpy. But this is as it goes into our turbine, so it makes a little bit of sense. Entropy as well. So I use S1 as an entropy variable, and so the S, I'm going to write entropy and then fluid T equals T1, P equals P1. So now I have enthalpy and entropy as state 1. H1, S1. Now for our equations. For Dr. Hagges' class, he always uses N minus out equals change, and that works pretty well. It makes it really easy. Mass energy goes into this turbine, work comes out, mass energy comes out, it equals 0. So how much mass comes in and out? Well, eventually we're going to solve for that. If I write m dot 1, the first m dot, because maybe there'll be more m dots later, times h1, so that's the enthalpy coming into the turbine. I'm getting work out, so I'm going to say minus w dot. You can use underscores to add words to your variable to make it really long and nice, because otherwise it just looks like w dot out net. Like, this is just too many words together. So w dot out, and do another underscore 1 2. This tells me that's the turbine at 1 2, and it's out, which is useful when I'm going to have 6 turbines later on. I'm also going to throw a minus sign m dot 1 because it's the same mass going in as going out, but now it's leaving at state 2 enthalpy, H2. Unfortunately, if you look at this equation, m dot 1 is an unknown, w dot out is an unknown, and H2 is an unknown. There's 3 unknowns in one equation. We can't solve that. In this thermodynamics class, if you ever have a Q or a W, you won't calculate it. You'll always solve for it, or you'll have to have an assumption that one of them is 0. For example, if I assume that there's also a minus Q dot out 1 2, I would have, eventually I might have an H2 and I'll have an m dot, but I'll always have these 2 unknowns in the equation, and I can't calculate the heat transfer in this class. So I'm going to assume that the Q dot's out or in on pumps and turbines is 0, because I need to calculate the work. And on heat exchangers, I'm going to assume there's no work, because there isn't, and the variable I'll solve for is Q dot. Back to this equation. Eventually I'm going to solve for an m dot, but just to make sure this equation works, I'm going to give it a fake m dot like Dr. Hagges suggests, and just call it m dot 1 equals 100. Now if we try and run this, we have 11 equations, 12 variables. We still don't have H2. Now we need to bring in component efficiencies on pretty much every working device. And how I'm going to do this is simple. The perfect pump or the perfect compressor or perfect turbine produces no entropy, which would state that the entropy at state 2 is the same as entropy at state 1. So if I have H2 perfect, so this is just a variable name, the perfect enthalpy would be the same fluid. I'm going to use the P equals P2 because the turbine would lower the pressure, compressor would raise the pressure, pump would raise the pressure. I'd have a second pressure. So I'm not going to use P1 at the state 2. I'm going to use pressure 2. And I'm going to use the entropy at state 1. What I could do instead is say the entropy at state 2, perfect, would equal the entropy at state 1. And I could change this to say entropy at state 2, perfect. Now if everything was perfect, I would get this H2. This is not the same as the real H2, the real enthalpy. So I'm going to come down and say efficiency. Well, first I'm going to do, I guess, a conservation of mass equation. It's going to look really identical to this one. Unfortunately, though, the H2 over here is going to be H2 perfect, because this is the perfect equation. And I can't use the same variable name here, so the W dot out perfect 1, 2, 2. So it still comes in at H1 always. And if we had a perfect workout, it would leave at H2 perfect. But now, this equation, we would have m dot 1, it's a fake number. We have H1, we have H2 perfect from here. We're solving for W dot out perfect. I'm going to use efficiency that I defined earlier. Now, efficiency of a turbine. So the perfect turbine is going to get more work out than a not perfect turbine. So if this side is 0.8, I'm going to times the bigger number by 0.8, I'm going to get less. So the real work, W dot, and sometimes I call this real to make it a little bit more sense, is going to be on top. I'm going to divide it by W dot out perfect 1, 2. So now I have W dot out perfect, and I have an efficiency I've defined at the top as 0.8. I'm getting W dot out 1, 2. Now I'm putting W dot out 1, 2 into this equation. I have H1, and I have an M dot 1 that's fake up there. I can solve for H2. Let's check. 15 equations, 17 variables. So I'm obviously missing something here. Let's double check. I could have typoed something. Efficiency turbine. I'm just going to copy this and paste this. And then W dot out perfect, W dot out perfect. W dot out 1, 2. It's pretty easy to typo stuff. But M dot 1 is given. H1 is given. M dot 1 is given. H2 perfect is given. Efficiency of the turbine is given. And I know this out perfect. So I'm solving for W dot out 1, 2. Now that I know W dot out 1, 2, H1 and M dot 1, and M dot 1, I should be solving for H2. And the S2 perfect equals S1, and I'm calling H2 perfect off of this. It's one of those times where you just get a little bit stumped. You can bracket out your equations, double check. 12 equations, 14 variables. So this block is not my problem. Something up in here. P1 is defined, T1 is defined. So H1 and S1 are both defined. I'm just going to go ahead and drop this out. Although I get the feeling that it's a little bit taller. S equals S1. Let's check this. 11 equations, 13 variables. So that's not the problem. Well, when in doubt, block off more equations. So square brackets, check. Okay, so it's not anything above this. It's somewhere in here. H1 equals enthalpy, fluid 1, T equals T1, P equals P1. Let's see if this one is our problem. 9 of 9, so that's not our problem. See, moving down, that's not our problem. H2 perfect. Oh, I see what our problem is. This is why the brackets help. I forgot to write enthalpy, so I was not even solving for H2 perfect there. Well, now I have H2 perfect. H2 perfect goes into here. I have M dot H1. I'm solving for my W dot out perfect. Now I have W dot out perfect efficiency turbine. I'm solving for my real workout. Now that I have my real workout, I'm solving for my real H2. This is why you do this in steps. I'm going to condense these variables back together. I like to keep all my state variables at the top. I keep my equations together like this. State 1 and 2 is done. Would have been a lot quicker if I didn't typo. There's a lot of typos always. State 2 to 3, heat exchanger, condenser. I don't know. Throw in some words. Phase change. Make it. Give it a little bit of description. So state 2 has already been defined. We have H2. It's solved for right here. So we're going to bring H2 in. I need to know H3. Well, H3 equals enthalpy, fluid, $1. Let's see, what do we know about state 3? T equals 108. And now let's just try this. P equals P2. Because the pressure 2 and 3 are the same. Now you would think this would work, but if I drew the TV diagram, I don't know if maybe I can do that really quick. You'd see a pressure line like this, and here's the line is the pressure. This whole line is a constant pressure, and so the T is over here. But this is all the same T, and this happens to be 108 degrees at P equals P2. So what you're telling E's is that you're somewhere in this region. So if I hit run, it's gonna not go. Oh, you can't do this because it can't know which part of this region you're at. However, you know that you need to send liquid to pumps. So instead of P equals P2, I'm going to tell it X equals 0, which tells E's over here on this TV diagram that I'm right here. I'm liquid. 108 degrees Fahrenheit, all around the left side. Now H3 will be solved for, which is 76. All right. So now we have H3 over here, and we have H2 from the previous equations. There's no efficiencies with heat exchangers. You don't have to worry about that little equation there. Let's just do our basic conservation of energy equation that, like Dr. Hagges writes, m dot 1, so our mass comes in, times H2. And this is a heat exchanger. This is cooling the liquid. The energy is leaving. So minus Q dot underscore 23 out. This is pretty descriptive. It tells me where my energy is leaving, the 2 to 3, and it's out. I'm also going to do a minus sign m dot 1 because our energy leaves, and now it leaves at state H3 equals 0. Wow, one equation this heat exchanger solved for, the Q dot out. Now this is with the m dot equaling 100, which is not true yet. Let's go on to states 3 to 4, the pump. Work in. So our pump is going to be similar to our turbine. We know one thing about state 4, which is pressure. And we know a lot of stuff about state 3. So let's define our state 3 stuff. So we can write our perfect, well, let's get our entropy. Now I could put my entropy right here or up in here, doesn't really matter. They're both dealing with state 3, it makes a little sense. But let's just say entropy of 3 equals, I got entropy fluid variable. Let's see, state 3 where T equals 108. And we're also, let's just use the conditions we used for our enthalpy X equals 0, because if we used P, we would run into that same error again about where in the two-phase region we were at. So our entropy at state 3 in the two-phase region. A perfect pump is not going to raise our entropy. So S4 perfect would equal S3. You don't have to do this step. But H4 perfect is going to be enthalpy, fluid 1 cache. Now T, well, I don't know the temperature after a pump, so I can't use T. But I do know the pressure after a pump. And it's going to be P equals, I'm just going to do P1, which is the 1250. I could write P1 equals P4. I'm also going to do S equals S4 perfect, although I could have just wrote S3. This step helps you keep in your head what you're kind of really doing, because a lot of your guys' code is crap. You can't read it. H4 perfect. So now I know the perfect enthalpy after my pump, and I know my enthalpy before my pump, H3. So let's go ahead and write our equation. I'm going to put a little space. I like to leave a little space between my declared variables in my equation. M dot 1 times H3. This time I'm going to put work in, so plus W dot 23, nope, not 23. I'm doing state 3 to 4 now. N. Then minus M dot 1 times H4, but it's not really H4, it's H4 perfect. And I should go back to that work. It's not really W dot 34, and it's W dot 34 perfect N. No, I'm solving for W dot 34 perfect N. I know what the perfect enthalpy and what my real enthalpy N was. Let's hit solve. W dot 34 perfect N. It's a positive number, which I would expect. But I'm not really putting perfect amounts of work in, so efficiency of pump equals, I'm going to copy paste this one in, so don't typo it. Okay, so a perfect pump would do less work. This number over here is like 0.8. So if I take 100 times 0.8, the right side of the equation is going to be 80, which is smaller. A perfect pump does less work, so now I'm going to put the real pump on the bottom. W dot 34 real N. So W dot 34 real N is going to be, let's check. W dot 34 perfect N would be 372. Real would be 460. A real pump works harder. Just like a real turbine gets less work out. Just write my equation again. This time I'm using real stuff. So M dot 1 H3. We come in at H3. We do real work N, 34 real N. And we leave at H4. This is the real H4. We're solving for H4 with this equation. H4 is solved for. H4 and H4 perfect. H4 perfect is somewhere. H4 perfect right here. So H4 is a little bit higher than H4 perfect because we put a little bit more work in with our friction and our pump. So 3 4 is pretty much done right there. Generally with the pump, a turbine, or compressor, you're going to have the perfect conservation energy equation, your efficiency, your component efficiency. Which one's perfect goes on top or bottom. It matters if it's a compressor or a turbine. Sometimes the perfect work is smaller because it would be easier to do the work. And sometimes it's bigger, it gets more work out. Then we do our conservation of energy with our real work and solving for our real state 4. Now we need to tie it back around. So I'm going to do comments so that 4-1, heat exchanger, evaporator, boiler. Just give some descriptions. A heat exchanger, these ones, there's no efficiency to worry about, so let's just go straight to our conservation of energy equation with a heat exchanger. M dot 1 times, we come in at H4, which we've just solved for. And this one, I'm adding Q dot. This is the boiler. I'm sending energy in, so I'm going to say Q dot underscore 41 in. Just gives me some good description which state I'm at and whether it's coming in or out. Minus M dot 1 times H1 equals 0. Now H1 and H4 are known. M dot 1 is kind of known right now, and Q dot 41 in. So that's perfect. Now let's see if I can. Lost track of some stuff. Alright. So this system technically runs with an M dot of 100. Let's find out. We wanted a network of 70,000 kilowatts, this is an English unit, so this enthalpies are calling in BTUs per pound mass, and they're timesing by pound mass per second. So I'm really getting BTUs per second, which is you can convert 70,000 kilowatts to BTUs per second. I can't remember the exact conversion, so we're just going to say we're going to be making 70,000 BTUs per second today on this one. So you can't use this code for your class, even though we've already handed the project in. Net work. So our work that we can sell is the work that we made minus the work that we used. The W dot out 1, 2 from up here. Not the perfect, it's what we really made. Minus how much we used. So W dot N. So here's our 3-4 pump. I can see this nice blue. Go down here, W dot 3-4 real N. Minus this. Now I can find out how much network I made. Network, 44,000. Well, that's not 70,000, and the project needs 70,000, so our M dot is wrong. Now I could say, let's just change M dot to 110. Run. Oh, our network is still not quite there. Instead of changing our M dot to 110, I'm just going to bracket out our M dot. Now I won't be able to solve it because I don't have enough variables. 23 equation, 24 variables. But what I can do is I can say, well, network equals these two things, but network also equals 70,000 BTUs per second. Really, I could just replace this with 70,000, and then now it will be forced to solve for the M dot 1 that would give it 70,000 network. If I hit enter, network 70,000, it was declared stated variable. M dot 1 is over here at 156.8. So that is how much fluid we have to move to make our system perfectly modeled. So this was project part 1 right there. You can right click this, and I can change the background to like green, which kind of helps you when you color print this. Lets you pick out like Q.N. I'm gonna maybe make this red, so I can just kind of look down and immediately go, oh, this is how much fuel I had to burn. This is how much M dot I was moving. Efficiency, let's call it cycle efficiency. Make it pretty descriptive. Equals goal over cost. Our goal is our network divided by our cost, which is how much coal energy we're burning. So heat exchanger boiler, we use this variable Q.41N. Divide by that. Cycle efficiency. Let's go check out cycle efficiency right here. 0.32. I'm going to make this foreground like blue. Bam, there's your cycle efficiency. 32%, which is what most people should be getting in this with these numbers. Somewhere around there, plus or minus a little bit. When you go to print this, make sure that you print it with equations and solutions, just this. You can select your printer and change it to a PDF printer and print it as PDF, which is what I do. I print mine in color. And that was how you did Project 2 Part 1 for Dr. Hegge's class. Some other things functions that you might have needed, well, we knew pressure and enthalpy and entropy. There was temperature, so I can check my temperature. T4 equals temperature. And fluid variable, I need to give it two conditions at least. So let's look at state 4. State 4 we had S4 perfect. Well, that's not what we want because we're not really at perfect. We're at H4. So let's give it H equals H4. And we need one more, P equals P4, but I never wrote down what P4 is. I used P1 because P1 equaled P4, so I'm just going to write down P equals P1. And then let's run this again. T4 equals 109. So we went from 108 degree water before the pump to 109.4 degree Fahrenheit water after the pump. The pump warmed our water a little bit, which makes sense. It shouldn't be going down. I have no negatives on my screen here. This is pretty finished Part 1 code. These T4s, I'll do these as I go along. I'm going to delete this. I'm going to move this into right after our pump. So sometimes after my equations, I'll throw in some checks, and I could even write this to T4 check or test to draw my attention to it in the equation screen. T4 check 9. I would go back to my diagram and I'd write 109.4 when I hand this in to Dr. Hegge. He'll be able to look at my diagram, he'll be able to look at my code, and if he wants to look at the 3 to 4 pump work in right here, he wants to say, how did I figure out that 109.4, and he'll see that, oh, the T4 check right here, temperature at enthalpy 4, P equals P1. See that he might be a little confused why I think P equals P1. So maybe I would have wrote at the top or right above it, P1 equals P4. Maybe in here I'd write P4. And then he could check out your answers. And you could get 100%. That's going to be it for this little video. I might do another one later on for different parts of the project as they are finished, and maybe help people out.